So we'll start this lecture on signal handlers. So we will see that signals are very different from what we have discussed in the past. So in the past, we have discussed system calls, interrupts and exceptions, which were means for the application to send something to the OS, to send either a command or some information to the OS. So that was a system call. And even an exception is also when the application does something and something goes wrong. When the hardware sends a message to the OS, that was an interrupt. Needless to say, these were messages that were going into the OS, right? And OS in this case means the kernel. But if you look at signal handlers, the direction of information flow is reverse. It is from the kernel to an application. So in a certain sense, we are reversing the flow of information, and the application has to somehow handle with the signal and deal with it, which means we'll have to introduce something called a signal context, right? An additional context, the fifth context. So we will talk about it. But the key idea is that a signal is different from everything else that we have studied in the sense that the flow of information is reverse from the kernel to the application, and that is why they are unique as well as different. An example of this could be that you move a mouse, and then what happens is that an interrupt gets sent to the OS. The OS figures out the displacement, horizontal displacement, vertical displacement, and this is wrapped up in a signal and sent to the application, and the application does something with the mouse, right? So either moves the cursor or it does whatever it wishes to do. So this information is sent back. So this is an example of a signal, and most graphical applications use signals a lot. They have to. So anybody who deals with hardware has to deal with signals a lot. So let's look at an example code with signal handling. So we will understand this in a reasonable amount of detail. So you have a main function. So let us go over it line by line. So consider this line, we are not doing anything. We are just declaring a bunch of variables, a child PID, a waiting PID, and a status. So we'll see what they mean in due course of time. So then what we do is we register a signal handler. So registering a signal handler basically means that we are saying that if we get sig user 1 is a custom signal. It is not a system defined signal, but you can use it for anything that you want, any custom purpose. So with sig user 1, we are associating the function pointer handler. So essentially the application is telling the kernel that if sig user 1 is raised, kindly invoke the function handler in the applications, in the user space. This is the function handler. So every signal handling function has the same signature. It does not return anything. It has a single integer argument, which is the signal number. So then it basically says that I am in the signal handler of this process, where %d, so get PID is basically a library call that wraps a system call to get the process ID of the current process. And that is what I print and I exit. So pretty much the signal handler, that's the only job that it does, that it catches the sig user 1 signal, it prints the process ID and it exits. That is the only job. And every signal handler has to be pre-registered with the OS, which your signal call does. And you pre-register it against a signal number, which in this case is sig user 1. Then what we do is we fork. So when we fork, we do separate things for the parent and the child. In the case of the child, you just print I am the child and I am stuck, in the sense you go to an infinite loop. So this is an infinite loop. So what the child does is the child prints a message and then it starts infinite looping. right? The child is stuck in an infinite loop. On the other hand, the parent sleeps for 2 seconds. So it sleeps for 2 seconds basically means that it tells the OS that wake me up after at least 2 seconds. And then, the OS can either set a timer or set an alarm, as we have discussed. And then the parent will get woken up. The reason for sleeping is you want the child to be set up, right? So you're sleeping for some duration such that the child is set up and the child has gone into the infinite loop before you start the rest of the processing. Otherwise, there is a risk that the child may not be set up. So even 2 seconds, there is no 100% guarantee the child will be set up. But let's say in this case, this is a representative example, and we want to wait for a long enough time where with a very, very high probability the child would be set up. Then what we do is that we would have the child PID. So we send a signal to the child PID. Sending a signal is done via the kill system call. You may want to argue with me and say that sending a signal should be the signal system call. Well, but for historical and legacy reasons, it is not like that. The signal call actually registers a signal handler, right? So ideally speaking, this should have been register signal handler, but that's not the way that it is. So signal call registers a signal handler, and the kill call actually sends a signal. I would have preferred register signal and send signal, but that's not the way it is. So the kill call basically sends a signal to the child process PID, and the signal is sig user 1. All right. So because the parent knows the PID of the child, so it sends sig user 1 to the child. So once that happens, the parent waits for the child to exit. So basically, the parent would like to see the exit status of the child. So it basically sends an integer, and so that will, and WPID is essentially the waiting PID of the child, the one that exited. So we will discuss this in a second. But what happens is that when the signal goes to the child, because the signal handlers also get copied, right? In any fork, even the signal handlers get copied. So the child enters this function, this line is printed, and then the child exits. All right. Then the child exits. And the moment the child exits, the parent's wait call gets released. Because the parent was waiting on the child and the child exited. So the parent's wait call gets released. So the parent prints, this is the child. The child is the child PID. The wait call that exited, the PID that exited is WPID, and both of these should be the same in this case. And the exit at the status, this is the status, this is exit status. All right. So this is an example of a simple signal-based interaction between the parent and the child. So of course, the way that the signal is being sent is via the OS. So you're not sending it directly, you are sending it via the kernel. So in a certain sense, you can say that either one process is signaling another via the kernel or the kernel is doing it directly. Both are equivalent. But basically, some information is going from the kernel to the user process. And this is the signaling mechanism from the point of view of C code. So the output of this will be like this, that the child will print, I am the child and I am stuck over here. Then the signal handler will be called. So you will print in the signal handler of process, that's a 1078. And finally, the parent will exit. So the child PID and the PID that exited should be the same, and they are the same. The exit status is 0 means all good. All right. So the sleeps statement that we added is just to ensure that the child is set up. And the parent side is that under normal circumstances, the exit status should be 0 and the wait should return the PID of the child that has exited, which in this case is happening. So you are welcome to run this code and check what is happening. So if we look at common signals, so this is what they are. So basically, we have all kinds of signals. So then, you have sig wait and sig, sig ill is basically an instruction that is not properly formed. Sig abort, sig FP, we have already seen the division error is a part of this. Sig user 1, we have seen. All right, sig kill is to terminate. Sig seg V is your segmentation fault that you routinely see in C programs because you access some illegal memory address. That is what it is. But there are a bunch of other signals like sig alarm, which is when your timer expires, right? Sig child, we have seen the one that is sent to the parent when the child exits, right? Sig cont and sig stop, we have seen stopping a process, resuming it. So we have seen many of these. So we have seen two versions of stopping actually. Sig stop and sig T stop. One is like a hard stop and one is a soft stop. So we have seen many of these signals in our previous few lectures as well. But broadly speaking, this is a list of signals, and there are two signals which don't have any connotation associated with it. One is sig user 1, the other is sig user 2. They can be used for anything that you wish, including inter-process signaling. So sending a signal, so this registering part we have seen to some extent, we'll look at it even more. Sending a signal has three main variants. Kill. So what kill does is it sends a signal to a full thread group. If there is a group of threads, it is sent to the entire thread group. When you do T kill, it's like thread kill. It is sent to only a single, only a specific process, a specific thread basically. And TG kill, so what happens is thread IDs can get reused. So TG kill is slightly more specific. So it ensures that it is like a safer version of T kill, where you are ensuring that in case these IDs are reused, it is still safe. So you can look at the man pages of these, but this is the broad idea that in general, when you send a signal, it's sent to every thread of a thread group unless you use a very specific form of the signal. So now let us look at many of the subtle aspects of signal handling. So if a process is not executing when a signal is sent to it, so let us assume that the process is not running. So signal is queued to be delivered later. This happens exactly the same way as interrupts, where an interrupt is queued to be delivered later. The same way that interrupts can be blocked and unblocked, masked and unmasked, signals can also be blocked as well as unblocked. So then what happens is that whenever anything is blocked, any signal is blocked, it is simply queued. And then when we unblock that signal type, the signal is then delivered the same way that an interrupt is actually delivered to the kernel. The logic is the same. Similar to soft IRQs, we cannot have two pending signals of the same type pending for a process. That is not allowed. Which means that if a processor is sleeping and you do repeated events, right, and repeated signals of the same type are sent, that then you can't have multiple signals of the same type. So think of that as a safety to kind of limit the storage sizes within the kernel. All right, so this is a restriction. Furthermore, what happens is that when a signal handler is executing, let's say for some signal, sig user 1, it blocks the sig user 1 signal during the period of its execution. All right. So that is why you actually define two sets of signals. So let's say that you are genuinely not interested in some signals, so you call it real blocked. When you are executing a signal handler, the signal that you are executing it for, that is temporarily blocked, but you could block a few more. So if you XOR this with what is called the signal mask, then you kind of get the current blocked. Right? So is that clear? So this basically means that you want to discourage the concurrent processing of the same signal. All right? And that is mainly to avoid race conditions and to keep things simple. So that is why such sort of a restriction has been provided. to ensure that multiple handlers of the same type are not executing concurrently. That's the main spirit of this law. Furthermore, when I send a kill signal, which means I want to finish it off, it is sent to all the threads in a thread group. But other signals are handled by any one thread. All right. So basically, when I would like to slightly correct what I said over here at the kill part. That when you send a signal to a thread group, it essentially chooses one of the handlers and it runs them, chooses one thread and runs them. So I stand corrected when I said everybody handles them. That's not correct. So only one of the threads in a thread group handles the signal. It makes little sense for everybody to handle it unless you are trying to terminate the full set of threads in a thread group. And signal handlers are shared within a thread group. But in any case, in a thread group, because the entire virtual memory space is shared, a lot of resources are shared, and signal handlers are one of them. So the take-home point from, let's say, this slide is that we discourage concurrent signal handling for the same signal, right? That is point number one. The point number two is that when you are considering a thread group, you would want one of the threads to handle unless you specifically say, I want this one. Right? And sometimes what happens, because IDs get reused, there is a safer version which is TG kill, right? Safer in my view. And the third thing is that if I want to terminate, which means terminate the entire thread group, then there is a need to send the kill signal to every single thread. Is that fine? So now let's look at how do you deliver a signal to a process. So what we have discussed earlier is that a signal handler is registered by the process with the kernel, where you are telling the kernel that in case this signal comes, you call this function. That is what registering means. So again, as you can see, the main thing that is coming into the picture is a function pointer. So signal handler is what? It's a function pointer, right? So what we are seeing in this entire course, especially in the last 5 lectures, is that the function pointer is emerging as an absolute first-class citizen in kernel design, right? Function pointer is by far emerging as the biggest concept. Fair enough. So the available options for us are like this, that whenever a signal is sent, either I handle the signal if a handler is defined, or I do some default action if a handler is not defined. It's the same as exceptions. So one is if it's an unimportant signal like SIG user 1, then I simply ignore it because no handler is registered for it. I can ignore it. It's unimportant and no handler is registered, ignore. If there are signals of the type like SIGINT and so on, then I need to kill it. So some signals, you can't actually ignore it. If you have to terminate, you have to. In some cases, you want to dump the core and create a core dump file. So you would have seen these files get created after a segmentation fault, right? So what they do is they contain an entire memory image and state of the process, such that you can open this core file in a debugger and inspect the state of the process. That is why this core file is created, because when it crashed, you would like to open it and see what your variables were looking like at the point of crash. So sometimes what happens is, especially in a segmentation fault, it may additionally create a core dump file, all right, which is of, you may not have realized it, but anytime that a C++ program crashes and a core dump file is created, that is openable in a debugger, and you have symbols enabled, you can see that, why did it crash? What were the values of the variables that led to a crash? So there must be some null pointer, so you can figure out what was null and what were the values of the other variables that could potentially allow you to find the bug. So the other is kind of a SIG stop kind of signal, where you stop the process. So we have seen a hard stop, this TSTP kind of thing, where you press Ctrl Z, and also, that's a soft stop, and then a hard stop where you send a SIG stop signal. So in that case, you stop the process and then a SIG cont will resume the process. So these are all the kind of default actions that you do. So in some of these cases, especially in a very high priority signal, you can't actually define a handler and kind of like ignore it, right? An empty handler is tantamount to ignoring the signal. But many of these cases, if you want to terminate the process, so that is not allowed. Because otherwise, if you think about it, if I handle all process termination signals, then my process will never terminate. So then my entire system will get destabilized, right? And of course, if the signal is handleable, if it's possible to handle it, then of course I handle it. But there are some signals, as we discussed, like sig kill and sig stop. They cannot be ignored, right? They cannot be handled and they cannot be blocked. They have the highest priority of all. And the idea is very simple. In one case, regardless of everything else, I want the entire process to terminate. If that is the case, it makes no sense to ignore, handle, or block it. In the other case, in the case of sig stop, I want the entire process to stop. This also is not ignorable, handleable, or blockable. So now let us look at the kernel code, given that we have a reasonably decent understanding of the application level. So what normally happens is that you define the signal is a kernel mechanism. In the sense, you need data structures in the kernel. And you also need data structures at the library level to help you implement, to help you write code like this. Does that make sense? That at the library level, unless you have, library calls like kill and signal and so on, which are wrapping the corresponding system calls, it will actually become very different, because we will see that the library calls also do a lot of additional work, right? So anytime you are wrapping a system call, you have to do a fair amount of additional work. So all of those things, the standard C library does for us. All right. And so this is the application view, something that a C or C++ programmer will see. And of course, JavaScript, Java, everybody uses the same mechanism. It is just they have different wrappers. And that wrapper, it may not be that apparent that you are wrapping a system call, as is the case in C. But again, the underlying code is the same. All right. So every language needs a library, and every library will do more or less the same set of things. So given that we have seen the application side, let us now see the kernel side of things. So let's look at the relevant entries in the task struct insofar as signal handling are concerned, and there are many such entries. So it's not a small entry, but there are many entries, and they have their relevant, relevant sets of importance. So the first is a pointer to a signal struct. So signal struct, as we shall see, is the apex data structure for signal related information by and large. So this is the signal thing. The second is a sig hand struct. As the name suggests, it's a signal handler structure which has information about signal handlers. All right. So one is information about signals and the other is information about signal handlers. They are kept separate. What is their structure? We'll look at it in a few seconds. Then we have blocked and real blocked. So as I said, real blocked is a real set of signals you are not interested. But when you are executing a signal handler, you have additionally blocked a few more signals. For example, the signal handler, let's say it is handling the signal sig user 1. It has additionally blocked sig user 1. You could have blocked a few more also. So blocked is a superset of real blocked. All right. So in general, if you are not handling a signal, blocked and real blocked can be the same. But otherwise, you could have some additional signals in blocked which are not there in real blocked. So far, so good. Then you have a structure for pending signals, all the signals that are pending and have not been delivered. So now this is an important part of the signal context that we need to understand. So let me explain it in a simple way first. We will discuss this in more detail. But the key idea is assume a single-threaded user process. It has registered a signal handler. Now a signal comes to it. If a signal comes to it, what do you expect the user process to do? In a certain sense, it has to now take on the role of an OS, where the OS basically would kind of run it on a separate thread with a separate stack and so on, right? If you recall, the OS assigns a kernel stack and then runs a handler. So the user process, in a certain sense, has to do something of this nature. So the user process, the context of the user process has to be stored. So you have to do some sort of a context switch in user space. That is needed because it was doing something, it has to stop what it is doing and it has to run the signal handler. So if it was executing user code, it will have to save the context somewhere, all right? And then it needs to execute the signal handler. And signal handlers execute in user space, all right? Then it needs to, so it meaning it or the kernel someone, right? It means the system. The system needs to restore the context and then the user code can start running as if nothing happened. So pretty much this is like an interrupt in the user space where you stop it, you run something, restore it. When you're running the signal handler, what stack do you use? Whose stack do you use? There are two options. Either you use the same user process stack and just grow it and then shrink it. Option 1. Option 2 is that you use a separate stack, right? An absolutely separate stack, the same way that an absolutely separate kernel stack is used, you use an absolutely separate stack. So in this case, you will have a stack pointer and the allowed size of it. And this you can run it on an alternate stack. Well, alternative stack, not alternate, but alternative stack. All right. So the point here is that we are trying to do something in user space that we were doing in the kernel space. In the kernel space, we are kind of using the same user thread, promoting it to a kernel, and then kernel thread giving it a separate stack, making it process the system call. In this case, the same user thread, its state is saved, context is saved. You run the signal handler either on the same stack or on a different stack. Right, the different stack you can kind of set that up. So in the signal, when you are registering a signal handler, you can specify use the same stack or a different one. Then you restore the context and you continue your user code. All right. So these options are there, but pretty much what you are understanding now is that a signal handler is architected sort of the same way as parts of the kernel. The signal handling system. So we will discuss signal struct first. So signal struct is like this, that a signal, as we have seen, is something that is shared across a thread group. So in a large part of the architecture of the signal, the fact that there is a thread group plays actually a central role because all the threads in a thread group share it, and Linux in general does not care about threads because every thread is treated as a separate process. But in the case of signals, an exception is made. That is when you actually look at thread membership in a thread group. That's the only point of time where you take these things ultra seriously. So the atomic T is nothing but an atomic integer. Live means the number of active threads in the thread group. All right. Then what you have is that you have all your threads, you organize them as a linked list. In this case, a doubly linked list. So all your threads are organized as a linked list. Then, if you have any of these, so as I said, any thread is a process. So I've used the word process here. if any of them is waiting on the wait system call. When do you wait on the wait system call? When you are waiting for a child to exit, right? So if any of them are there, then you add them to a wait queue. So a wait queue contains all the threads that are waiting for one of their child threads to exit. And then, if you are considering a thread group, as I said, when you send a signal, one of the threads handles it. So you maintain the information that which thread was the last to receive a signal and handle it. So then that can be cur target. Finally, every thread group will have a list of pending signals, which is a shared list. And so that struct sig pending is that shared list of pending signals. All right. And all of this information is shared by the entire thread group that Linux treats to be an atomic unit insofar as signals are concerned. And as we have said earlier, unless a specific thread is mentioned, right, unless you maintain a specific thread whose process ID is unique, then if you send it to a thread group, generally if you send it in the direction of a thread group, only one of the threads will handle. And that is, and you are maintaining a pointer to which thread was the one that handled the signal the last, right? That information is being held over here. So broadly speaking, this is your signal struct, which is maintaining some high level information about a thread group with respect to signals. All right. So now let us look at the next one, the sig hand struct, right? What does that do? So what that does is reasonably interesting. So here also, all the threads in a thread group share the same signal handler structure. And let us look at the first one. It's a reference count. So as we have discussed earlier, a reference count is a very important concept in the kernel because it basically maintains a count of who all is pointing to you. When the reference count is 0, you know that you are not relevant anymore because no one is pointing to you. So essentially, you can be garbage collected. That's the big broad idea of having a reference count. It indicates your importance. The moment no one references you, you know that you are absolutely redundant. So count maintains the number of task structs that actually point to this handler. In the sense, the handler you must have registered, right? In how many task structs have you registered this handler? So this count is maintained over here. Then what happens is that there are two ways of sending a signal. There is a normal way and there is a special way. The normal way is you tell the kernel that I want to send a signal to a certain process, or the kernel receives an interrupt and it decides to send a signal to a certain process. That's the normal way. The other way is, if you consider inter-process signaling, then let's say process P1 writes something to a file. The fact that it has written something is treated as a signal, right? So in this case, it is actually being written to a file. From the file, the signal is being transferred to P2. This is, of course, being done by the kernel, but there is a file in between. All right. So this is known as a signal FD. FD means file descriptor. So this is happening through a file. So then you will have a waiting queue, right, of all the kind of processes waiting on the file. So that is this wait queue head T. So this is an alternative mechanism for signal handling. And finally, what you will have is that you will have this action array. This action array will have underscore nsig entries, and this is typically 64. Large array, 64 entries. And this is basically the point. This is your signal handling table, which means that you index this with the ID of the signal. And what you get is a sig action, which as we shall see, kind of wraps the pointer to the handler. All right. So this is similar in principle to your interrupt handling table, exception handling table, system call table, right? All of these things are using exactly the same architecture, which means if you understand the basic concept, you will be able to use it everywhere. And the core of the basic concept is that you have a table with a few entries, not many. 64, 128, 256, in this case 64. You take the index of something, in this case the signal number, access the entry. So if this is entry 37, you access the 37th entry. What is stored there is some sort of a structure. In the structure, you have a function pointer. And the function pointer is the one that is invoked. So pretty much the function pointer in this entire story is emerging as a first-class citizen, which of course is being wrapped in some structure and that is being stored in an array. So that is a little bit of software engineering which we should not be very seriously bothered about. But this is the core or crux of the idea. So the most important part of this structure is basically the array of kernel sig action structures, where a sig action, as the name suggests, wraps a handler. So k sig action actually wraps sig action, and sig action has three fields. The first is a pointer to the handler, essentially a function pointer. Then a bunch of flags, the way that the signal should be invoked, the way that you will enter signal context. And then, as we have discussed, that when a signal handler is running, definitely the signal that is being handled, that is masked. But you may want to mask a few more because you don't want to be interrupted in the middle of a handler. So the additional ones that you mask, that is the signal mask. So essentially, you have a basic set of mask signals, the ones that you are definitely not interested in. And then if you add SA mask, add basically means a logical OR. Then you get the block set. All right. So this is the idea that we have over here, that you have a set of block signals and then you block a few more during the execution of the handler to arrive at a superset. So the basic action we have seen, so the way that this is invoked is very simple. Well, we will see, again, it's not super simple, but we will look at the complexities later. But the idea is that every signal handler is a function pointer. You jump to the function, execute the function. But then there are complexities. Where does the function return to, so on and so forth. We will discuss that. But before we do that, let us look at the rest of the data structures. So what we have seen in the signal struct, which is nothing but it is a structure for the ecosystem of the signals, that so we have discussed almost everything. We have not discussed the list of the pending signals, right? That is one more thing. That's the last data structure we need to discuss. That we have discussed the handlers, but then you need something to store all the signals that are pending, right? So the ones that need to be handled. So as the name suggests, there is a struct called sig pending, and sig pending points to a linked list, mainly because you want to have multiple pending signals, and each pending signal is actually a sig queue entry. So this is where things get complicated, right? So I will not blame you if you are not able to understand this. A part of this is for the somewhat unconventional naming, and a part of this is because the way that linked lists are created in the Linux kernel. So the first is, you kindly don't look at the slide, just look at struct sig pending and the first member. This is pointing to a linked list, and as you know, a generic linked list in Linux has a next pointer and a previous pointer. So this is basically a part of the linked list, and in Linux, all the elements in the linked list need not have to be of the same type. There is no necessity. It is just you are supposed to know what is the type of a neighbor, that's all. As long as you know that, somehow you are good. So in this case, you have a linked list, but the elements of the linked list are actually these sig queue entries, where a sig queue is not a queue. Okay, so this is a primary source of confusion. This should actually be named sig entry, but since I didn't write the kernel, you can't blame me for it. I would have named it sig queue, but think about it as sig queue entry, right? This is an entry in a linked list, right? The queue is suggestive of a list, which it is not. It is an entry, and every entry to be a part of the list has to have a list member, right? That is how you are a part of the list. And we have, if you think about the class where we discussed Linux linked lists, we had a ABC and a DEF. They were of different types, but they were all on the same linked list. So this is exactly the same thing. This is why that was introduced, only for this. So what you have is similar to soft IRQs. You have 64 defined signals, and you want a data structure to say, is the 27 signal set to 1 or not? The standard way of doing this is use an unsigned long integer. All right. A SIG set is nothing but an unsigned long integer whose size is 64 bits. If bit number 27 is set to 1, it means that there is a signal pending for signal number 27 is pending. All right. And at any point of time, only one signal of a certain type can be pending. Similar to soft IRQs, that is why you use a bit vector, and the bit being 1 means the ith signal is pending. All right. And what you have is you have this linked list which corresponds to these pending signals. And each entry of the linked list actually has the sig info t. Sig info is signal information, which indicates the type of the signal. All right. So in a sense, if let's say the n bits here are set to 1, you will have n entries in this linked list, 1 per set bit. So just to go one step further, assume that there is some signal and it is signal number 19. In that case, the 19th bit in 680 signal will be set to 1, which means that this signal is pending. Which means that one of these SIG-Q entries will be for signal number 19. So let's assume that there are 5 bits that are set to 1 in the 680 signal entry. There are 5 bits set to 1 here, which means that there are 5 pending signals. For every pending signal, there will be one SIG-Q, which means if there are 5 bits set to 1, there will be 5 SIG-Qs in the linked list. And needless to say, SIG pending and SIG-Q are a part of the same linked list. And it's a doubly linked list. It's a circular linked list. So one of them is a SIG pending. The rest all are SIG-Qs. All right. So far, so good. So the entries are not the same. So let us understand this SIG info, signal information. So this is simple. The first one is the signal number. So if the signal was set for signal number 19, that is exactly what you store here. If let's say this arose because of some error like a segmentation fault or something, and if there is a unique error number, that is stored here. The source of the signal could be the OS, in the sense that you did something, some device raised an interrupt, the OS decided to send a signal. Or the source could be some other process that is sending a signal via the kernel, right? You can have multiple sources. So the source of the signal, the code of the source is the third argument. And if let's say another process is sending a signal via the kernel, then the sender's PID should be there, right? Who is sending a signal to you? So that should be there. So all of this information is there inside a signal information, which is wrapped inside a SIG-Q, right? So it is obvious that we want to create a linked list of signal information structures, but we didn't want to put a list head there. So we wrapped it in a SIG-Q, put a list head over here, right? So this software engineering should be clear what we did, that we created a structure and we created a linked list over there. And then we added a signal information. And the job of the SIG-Q was to serve as a wrapper. And the functionality of the wrapper is to provide linked list functionality. All right, so far so good. So these, so as I said, software design and making such choices, it's more of an art than a science. Because what happens is that one designer is creating something and the rest of the kernel developers are supposed to use it. All right. So efficiency is of course a topmost concern, but so is elegance. You want other people to use it seamlessly. You want them to use it elegantly, and you want them to use it in a certain way where the chances of introducing bugs is very little, right? So you also want them to use it correctly, where even the system is such that even if they are not great developers, the chance of actually committing a mistake is not much. So that is a hallmark of any good programming system, that the system is architected in such a way that even if you want to sort of introduce a bug, you cannot, right? So these are, some such things. So the idea here is that when I am calling a function, let's say kill function, to send a signal, and then the OS is sending a signal, you actually need a lot of coordination between the process, then library functions, and the kernel. All right, is that clear? So what is done is that in this case, if a user process is running, its context has to be saved. There is no point in saving the context in the kernel because the entire work is happening in the user land. So save it on the user stack itself, or save it on a separate stack if that is what was the original intent. So let us see what exactly is stored in terms of the context. So in terms of the context, see, in this case, it's not like a hardware context where you'll have to kind of store a lot of things, and that too in such a careful manner, but it's still a context nevertheless. So one thing that you actually store is a return address, which means that when you are calling a signal handler is a function. Where does the function return to? So it should not return to the point at which the user process got interrupted, because there is some additional processing, right? So you want the user process, then you want the signal handler to run, but then you want some custom code to run, right? Let's call it custom. So you don't want to resume the user process immediately, and the custom code will also include the restoration code for restoring the context, and then you want the user process to run. This basically means that when you are calling the function, you want it to return to some other point, correct? Not the point at which you forcefully invoked. So that some other point is a point that you will specify, and that is possible to do in the sense that in ISAs that use a return address register, you populate the register with where you want it to return to. In ISAs that use the stack, you add the return address to the stack. The return address is typically set to a specific GNU glibc function known as restore RT. All right. So essentially restore the restore return path of the signal. So the return address is set to a separate location in your glibc code, which will do some additional processing. That you can always do, because when you are invoking a function, the function is not in your control. But where it is going to return to is in your control, because that is something that you have pre-specified, right? That is the important insight. So in this case, like in x86, you put it on the stack, that is tantamount to pre-specify. And then it will return to wherever you want it to return to. We'll see what that place does in the next slide. Then you store the context. Context is not a new beast for us. We have seen it. So the context in this case, the U context is user level context. So you store a bunch of flags, then you store the stack pointer, and you take a snapshot of all the registers and the processor state. That entire thing you put in a user context. And clearly the stack is also coming in there, the point at which. So the entire thing you collect and put it in the user context. And this will also have a SIG-info. SIG-info is the same kernel SIG-info, the signal information, right? Why are you doing this in the first place? You are doing this because you received a signal. What is the signal number, details of the signal, all of that is over here. So what is the takeaway point? The takeaway point is you collect and save the context. That we knew. That has to be done. Otherwise, how do you run a signal handler? The takeaway point is that you are hacking the return address and sending it somewhere else to a place of your choosing. Right? That is the main thing, because your return address return semantics allows you to do so. Now, if you look at returning from the signal handler, what will happen is the signal handler will finish. Then it is going to return to this function because before invoking it, this is where you wanted it to return to. Restore RT is a general function. Its job is to collect if, let's say, any exceptions or something happened during the signal, look at how the handler executed. Then restore the context. So its biggest job is to restore the context. You restore the context and you make a sig return call, right? So you have to restore, but you can't restore the context, right? Essentially, the kernel has to do that. So you have a system call is needed. So you make the sig return system call, whose job is to restore the context and start the user process exactly where it stopped, right? So that requires kernel support, which is why the sig return system call does that. So what's the key idea? You follow the reverse sequence of steps, and then you use the copy from user function to copy the context from the user space to the kernel space such that the kernel can restore it, right? Because the kernel knows how to restore it. Then you restore the context of the user process, populate the registers, set the stack pointer, and the way that you restore yourself from a system call, the same way you restore yourself from a signal. And the user process after this custom code is going to start at exactly the same point. So this finishes our discussion of chapter 4. See, if I were to go back and look at the last outline slide, so we discussed broadly 3 things. We started with system calls, so we looked at a library call, traced the entire path of a library call, right? And we saw what exactly printf does. Ultimately, how does it translate to a system call? And what does that system call do? How are arguments passed to the system call via registers, via the stack? How does that work? So we looked at that. Then we looked at the interrupt architecture, which is actually quite elaborate in terms of APIX and LAPIX and IO epics and everything. We looked at exceptions. We looked at the methods to handle interrupts. That itself is even more elaborate, where we specifically looked at your top halves. We looked at soft IRQs. We looked at threaded IRQs. And we looked at work queues. So these are clearly different mechanisms with different trade-offs. So we looked at all of it. And then we looked at signal handlers, where signal handlers is more like a user space interrupt, where a user process is running, you stop it at one point, and then you run some handler, and then you finish the job, then you restore the context with, of course, some help from the kernel, and then you start that. So signal handlers are mostly useful for these GUI kind of software, a graphical user interface kind of software, where, in this case, if I'm writing, what am I doing? This is a mouse device, right? Think of it. So if I'm writing something like this, essentially, the interrupt is being captured by the OS and it is being sent to, in this case, PowerPoint via a signal mechanism. And PowerPoint is drawing this on the screen. There you go. That is signals. So the next chapter will be about scheduling of processes, which again is a second heart of the operating system.